Okay, I'm going to explain how to do general regions in calculus. So the first thing is now we're dealing with a function of more than one variable. So in this case, I want to find the volume of a cube. So here I have my cube, which is 2 units or 2 feet in the x-axis, 2 feet in the y-axis, and 3 feet in the z-axis, where z is a function of x and y. So at any xy grid coordinate down here, the height is always going to be 3. So common sense, if we want to find the volume of this cube, we're going to just take length times width times height, or 2 minus 0, 2 minus 0, and 3 minus 0, which gives me 12 cubic feet. I'm going to take what's this plane down here in the x and y plane, and I'm going to redraw it here. Okay, so now this is my same exact xy plane that I had previously, and now my z, or my 3 feet, is coming up out of the page. So to add the area up the same way, I can draw a line through the shape, and I'm going to add up the area in the x direction first. And what I want to know is what the equation of these lines are. So the equation of this line is x equals 0, whereas this is x equals 1. And the equation of this line is y equals 2, and this is y equals 0. My function was 3. My f of xy is a value of 3. And I'm going to add up the area in the x direction first, dx. Okay, so this dx corresponds to the first integral, and it's wherever the line touches first, going in the positive direction. So here it touches at x equals 0, and the second place it touches when it leaves the shape is x equals 2. And then the next direction I'm going to add up is in the y direction. And the y direction goes from boundary to boundary. That y direction is going to be 0 to 2, from a height of 0 to a height of 2. Now as I integrate this, I'm going to get 0 to 2, and then I have 3x, and I'm going to evaluate that from 0 to 2. Okay, this gives me 3 times 2 minus 0, and I'm going to integrate again with respect to y, which gives me 6y from 2 to 0, which gives me 6 times 2 minus 0, or 12 cubic feet, which is the same 12 cubic feet that I had up above. Now when we think of this in terms of units, the dx is in units of feet, the dy is in units of feet, and the 3 was also in units of feet. So if I multiply essentially those 3 terms together, I'm going to get cubic feet in my answer. And the important thing is that this lower limit here, this has to be a function, and it has to be in terms of x equals, because dx is my first operation of order of integration. Okay, this also has to be a function, in which case this is x equals 2. This was x equals 0. Okay, the outer integral, the 0 to 2, corresponds to the dy. Okay, this has to be a boundary to boundary. Okay, so let's apply the same concept to another problem. So given I want to add up the area of a function now, our function is y squared, which is a different surface height, and I still have to add up what is essentially this xy plane on the floor. So here this region is bounded by d. So d, I'm given these constraints. Y goes from negative 1 to 1, and x has to be from negative y minus 2 to y. So what I want to do is I want to extract these like equations, where this is really y equals negative 1 and y equals 1. So on my picture, I can just draw the equation of that line. where this is y equals 1, and this is y equals negative 1. Okay, my other boundaries here is I can grab this piece first, where this is just y equals x. And then this other half is going to be negative y minus 2 equals x. Or if I rearrange that, negative 2 equals x plus y, or y equals minus 2 minus x. Okay, so I have a negative x, which is a negative slope, and it's going to intersect the y-axis at negative 2, which is down here. Okay, so now you start to see the region we're bound by. So this is, my region has to be above this equation, so x has to be greater than or equal to the negative y minus 2. It has to be above this line, okay, in this direction. But it has to be less than this line, so it's in this direction, and it has to be below y equals 1 and above y equals negative 1. Okay. This is my region. So now if I want to add up the area in this region, I'm going to start off doing it the easy way. I'm going to do dx. Okay. In which case my integral will start with dx, and the first place that dx touches the shape is the equation. I have to put it in terms of x. So this, if I rearrange it, is going to be x equals negative y minus 2. So that becomes my lower limit. My upper limit, or the last place that dx leaves the shape, is going to be y equals x, or x equals y. Now I add up the area in the other direction, the dy, which is boundary to boundary. It's going to go from negative 1 to 1. Okay, if I take the same shape, okay, and I start to add up area in the opposite direction now. Let's say I want to, instead of starting off with dx, I'm going to start off with dy. Okay, if I slide this dy back and forth through the shape, the upper limit remains the same, y equals 1, but the lower limit changes from y equals negative x minus 2 to y equals x. And because the lower limit changes, I need to treat it as two shapes, in which case I'm going to have two dy's. So this becomes shape 1, and this becomes shape 2, where each has a dy and each will have a dx. Okay, so I have to add this up as two different shapes. So this will be shape 1. Y squared remains the same. Now we're going to integrate first with respect to y. This is dy. So the first place that crosses into shape 1 is the equation of this line in terms of y. Negative x minus 2. This has to be function to function. The second place that leaves the shape is y equals 1. And in the x direction, we go from negative 3 to negative 1. And then shape 2, first place dy crosses into the shape is y equals x. The second place it leaves the shape is y equals 1. Whereas the dx will go from negative 1 to 1. Okay. If I execute this integral, I'll get 4/3. And if I do both of these sum together, the sum will again be 4/3. And the answer has to be the same because we're adding up the same region. Okay, I'm going to quickly talk through a couple examples. So here's a type of problem where we're given the integral with the upper and lower limits already inserted, and we're asked to sketch the region and reverse the order. So the first thing to understand is that this first order of integration dy corresponds to the inner integral, and these numbers are in terms of y equals. So the first thing I want to do is extract boundaries. Okay, again, they're in terms of y equals. So this is y equals 0. So this becomes one of the equations in my line, y equals 0. I also have y equals the square root of x. Y equals the square root of x, and then I can rewrite this in terms of x equals y squared. Okay, this is a parabola that's just turned on its side. So here's the curve, x equals y squared, or y equals the square root of x, and here's y equals 0. Okay, these become our first two boundaries. Our next boundaries correspond with the dx with the outer integral, in which case this is x equals 0 and x equals 4. Okay, these are my next two boundaries. So here's x equals 0, and here's x equals 4. Okay, so as the problem is given to me, the dy is the first order of integration, so that's the line that crosses through the shape, dy. So the first thing that dy touches is y equals 0, the equation of that line, or that function, y equals 0. The second thing it touches is y equals the square root of x. And the boundaries go from 0 to 4. So that's sketching the region as it's given. The next thing is to reverse the order of integration. So given the same shape, now by reversing the order of integration, the dx is first, so that's going to go through the shape. Okay, and it has to go in the direction of the x-axis. So the first thing dx touches is this line, which is in terms of x equals y squared. Okay, so again, the invisible x is not written there, it's x equals y squared. And then the next thing it touches as it leaves the shape is x equals 4. So it goes from y squared to 4 as my lower limit to my upper limit. And my boundary to boundary, the boundary here is at 0 to a height of 2. And this will give us the same problem. Another common problem is that when you're given two integrals. So in this case, I'm given these two integrals, and I have to draw the region, and I have to reverse the order of integration and write it as one single integral. So in this case, this is two different shapes. So I'll start off with shape number 1. Okay, the dx gives me boundaries. Here is x equals 0, and here is x equals 2y. X equals 2y, or y equals x over 2. Okay, so I can draw that. Down here, I know here's x equals 0 is this line, and y equals x over 2 is this positive slope that goes up. So the run is 2 and the rise is 1. Okay, x over 2. Okay, so I know that this dx crosses through that shape. The first thing it's touching is x equals 0, and then y equals x over 2. Okay, so I know that somewhere down here, now I just need to know the boundaries. And the boundaries here, y goes from 0 to 1. So the height goes from 0 to a height of 1. Okay, so this becomes another boundary. So this is my first shape. My second shape, if I start off with the outside, my boundaries, dy goes from 1 to 3. So it picks up where y equals 1, and it goes up to y equals 3. And now this dx, this is x equals 0, which is this line again, and this is x equals 3 minus y. Okay, x equals 3 minus y, in which case this dx crosses through the shape, first touching the 0, x equals 0, and second touching x equals 3 minus y, and the boundaries go from 1 to 3. So as I reverse the order of integration, now I have to start with dy. Okay, it's the same shape. So my dy goes through the shape first, and the first thing it touches is this line, which has to be in terms of y equals, or y equals x over 2. And the second thing it touches as it leaves the shape is y equals 3 minus x. And my boundaries on the dx go from 0 to 2. And this will give us the same answer. And the important thing to remember is that the line that I'm drawing through the shape is always the first order of integration. And this line can be drawn anywhere in the shape. If I draw that anywhere in the shape, it always touches those same lower limit and upper limit. And the reason why we needed two shapes in this picture is because if I slide this first dx through the shape, as I cross this line in the middle, my upper limit changes. It changes from this line to this line. And because my upper limit changed, that's why I need two shapes.